So we have covered several examples where we considered the distributed load, whether a uniformly distributed or triangular or partly distributed load. Part of the beam is free and then you have a triangular load in between. Now let's look at some examples where we use the point loads and the point moment. So we have a simply supported beam, and we have looked at this example using the method of sections. We have a simply supported beam P as load P, and with a distance A and B separated by a distance. So here you remember that the reactions that we get at these 2 points, my RA, suppose if this is my point A and this is my point B, and where the load is acting is C, the load P. So RA is PB by L, and RB equals to PA by L over here. So let us draw 2 beams again for the shear force diagram and the bending moment diagram. So I'm going to draw my shear force diagram on this one and bending moment diagram of this one, right? So now this is the case where you do not have that uniformly distributed load, but you have a point load. And if you remember that from the different relationships which we had looked at between this load, shear and moment, one of them was for the point load. Now what kind of change did it cause? Just to jog your memory. So the situation was something like this, right? You had an element where we had V, and we had V plus V1, and we had M, and we had M plus M1, and these changes were happening when you had a concentrated load P that was acting. And if you remember, so this was a part of the relationship number 3. So what did we see in this? We had seen, and we are not going to go ahead and derive it, that your shear undergoes a jump. So V undergoes a jump, and in this case what we had was this V1. This jump means the abrupt change, right? So here you had a V, here you have a V plus, but in addition to this we have a V1 over here. So then this V1 was came out to be as minus P, which is like in the direction of the load that is there. So you have a further reduction that is there, because reduction is downward, because you're drawing the shear force in the top half, bottom half. So whatever is going down keeps going down, right? And also the moment M1 was your 0, so there was no appreciable change in moment. So it was M and M over here. So let's use this relationship to find to draw the shear force and the bending moment diagram, and we are going to make use of the other relationships as well. So here let's first draw the shear force diagram. So at the left end I do not have any option but to have this vertical reaction of PB divided by L over here. So let's just go ahead and draw that. So here I have a positive PB divided by L going up, right? Now remember that again, so think of the relationships. The one relationship is that dV dx is minus of W times x distributed load. Here you do not have any distributed load. So here the distributed load is essentially 0. So your your V is going to be a constant line, because the derivative of the constant is 0. So the V is going to be a constant up to the point of discontinuity here, that is P. So up to that particular point you're going to have a constant value up to this line C. Let me draw the guidelines again so that we are drawing neat shear force diagrams and bending moment diagrams, right? So up to this particular point, up to this point C, so this is my A and this is my B and this is my C over here. Up to this particular sorry, wrote that in the wrong order. A, B and C is over here. So up to that particular point I have this. Now here you see at P I have a point load, and when I see a point load I see the shear. So this is the positive convention for the shear. I see the shear goes a downward jump, but it reduces by a quantity of minus P. So due to this P, your additional shear that you get, V plus V1, it reduces by minus P. So here just when you go to the right hand side of P, whatever shear was there, the shear just to the right becomes V plus V1. So here already at V, I had a value of PV divided by L. So it is going to be PV divided by L minus P, because V1 equals to minus P, right? So the shear right just to the right will be my PB divided by L minus P, which you see comes out as P times B minus L divided by L, which is equals to minus of PA by L, because B minus L is the total length over here. So here you are going to get a downward jump. Downward jump goes to a PA divided by L. I'm drawing on the lower half plane, so I'm not marking the negative sign over here. So from here, I do not have any other distributed load or anything. So again, I go back to this condition that it is 0. So it is going to be a constant line. So it goes as a constant. And then of course, here you have a PA divided by L. So it goes up here, right? So here you have a positive and you have a negative. Now this was my shear force diagram. And how is the bending moment diagram going to vary? Intuitively, I know that this is a pin and a roller, no externally applied moments over there. So I'm going to have at A and B, I'm going to have 0 bending moments. Now here at A and also the shear force is a constant, so that tells me, so let's just write that down, dm by dx equals to v. This is relationship number 2. So here your v is a constant, so that tells you your moment must be a first degree, right? And what is going to be the slope of that? The slope of that, and whether it's a positive or a negative, the slope of that will be the value of the shear at this particular point. So it is PB divided by L, and that stays constant. So you will have a constant linear line. So let's just till this point of discontinuity over here. So let's just draw that constant linear line, because I'm drawing the not constant, I'm drawing a linear line up to this particular point because I'm dealing with this over here. Now right at this point I have a load, but I know that there is not going to be a jump in the moment. So at this point the moment stays the same. So what is the value of the moment? If I have to find the value of the moment, this is my point C over here. Now remember, I can find MC minus MA will be the area of the shear force diagram between these 2 points. So the area of the shear force is PP divided by L times this distance, which is nothing but A. So it is going to be P AB by L, and MA is 0, so MC becomes equals to, so this value over here is P AB by L. Okay. Now from here I can see that you have a 0 moment at this particular point, constant shear force. It's going to be a linearly decreasing slope over here. So easily also again, and the whole shear force, a whole bending moment diagram is positive. So again, easily you could find the shear force and the bending moment diagram for this beam with a concentrated load.